Welcome back everyone. In this last lecture, we will complete the classification of finite dimensional semi-simple Lie algebras. So, by giving very explicit construction of semi-simple Lie algebras from given root system. So, for that purpose, let us first recall a result that we proved earlier. So, let us start with G being semi-simple Lie algebra. So, let G finite dimensional semi-simple Lie algebra and H being a fixed Cartan inside G. So, this is fixed Cartan subalgebra of G. So, then we have a root system phi. So, this is corresponding to the tuple G and H. So, with respect to the tuple GH. So, in particularly we have this Cartan decomposition, that is what we have seen. So, this is given by G equal to H direct sum of root spaces where alpha coming from phi. So, we also have a very special subset of phi called pi system, which we denoted by pi. So, this is set of simple roots. So, this is given by alpha 1 etc. alpha L. So, which is sits inside phi where L is the rank of the Lie algebra. So, which is also the dimension of the Cartan. So, now what is special about this set of simple roots? So, they satisfy two important properties. So, given any alpha in phi, so given any alpha in phi, alpha can be written as either non-negative linear combination of pi or alpha can be written as non-negative linear combination of elements of pi. And of course, pi is also a basis of our H star. So, because phi is sitting inside H star, so this is what defines simple roots. So, now we proved that existence of simple roots, and we also proved that any two different set of simple roots will be conjugate under the Weil group of phi. So, now because of this the associated Dynkin diagram or the Cartan matrix of this pi or the root system phi. So, that will be independent of the choice of the simple roots. Okay. So, recall we have defined this Cartan matrix. So, which is actually L by L matrix where ijth entry is given by this Cartan in number alpha I comma alpha j. So, this matrix called Cartan matrix of phi, and then what we actually proved, this is independent of the the root set of roots that we have chosen, the set of roots that we have chosen. So, in particularly if we actually put together one more result that we already assumed to be true, that any two Cartan subalgebras of G are conjugate. So, then this association of root system actually becomes unique. Okay. So, basically to associate a root system we made this choice of Cartan subalgebra, but we realized that that is actually independent of the Cartan subalgebra that we choose inside G. So, this association becomes unique, that is what we proved, and we also proved that if phi of G is isomorphic to phi dash of G dash, then G and G dash must be isomorphic. So, this association is actually injective map, that is what we proved already. So, now to complete the classification of the semi-simple Lie algebras, it is enough to prove that given a root system phi. So, one we have already defined root system in an abstract way. So, given a root system, if we prove that there exists semi-simple Lie algebra from which this root system is coming from, so then our story is complete. So, then the classification of finite dimensional semi-simple Lie algebras boils down to the classification of this finite root system, which we already did it. Okay. So, only the missing part is given root system. So, given abstract root system phi. So, let us say it is sitting inside some Euclidean space E. So, we need to say or we need to construct G, which is finite dimensional semi-simple Lie algebra and whose root system coincides with phi. So, this is the task. So, once we are done with this task, then the classification of finite dimensional semi-simple Lie algebras is equivalent to the classification of finite root system, which already we saw how to do. So, we also realized on the way, like any semi-simple Lie algebra can be written as a direct sum of simple ideals, and this correspondence that we have here that actually obeys the decomposition. So, that means the corresponding root system of G also can be written as direct sum of irreducible finite root systems. And so, if you look at the correspondence between this irreducible root system that comes from the semi-simple Lie algebra, you can see that the corresponding semi-simple Lie algebra should be simple Lie algebra. So, under this correspondence, simple Lie algebras maps to irreducible root system. So, in particularly if you are interested in proving that this association is actually surjective, that is onto. So, where the map is defined from the isomorphism classes of finite dimensional semi-simple Lie algebras to isomorphism classes of finite root system. So, to prove that map is onto, it is enough to prove that given irreducible root system, if we prove that there exist simple Lie algebras whose root system is coinciding with that given irreducible root system. So, but it is not that hard to actually construct for any semi-simple Lie algebra. We will actually do it in the generality, not a problem. But anyway, so here again, like, so this problem of constructing irreducible given irreducible root system some simple Lie algebra. So, again, like, one can go to the classification of irreducible root system. So, we know already that there are 7 types, okay, A to D, which is classical, and then E, F, G. So, where E actually there are 3 types of E, E6, E7, E8, and then there is F4 and then G2. These are called exceptional. So, given this list of irreducible finite root system, if you are able to produce actually the corresponding simple Lie algebras, so then we will be done. Okay. So, for the classical case, it is not that hard. So, I will actually add this in the assignment sheet, but for the exceptional types, okay, even G2 it is not that hard, but when it comes to E and F, it becomes very hard to construct this Lie algebras very explicitly. But anyway, so we will actually take this abstract approach. I will actually outline how to construct semi-simple Lie algebra from a root system. So, that actually uses what is called Serre presentation. before getting into representation, we need to understand why that is motivated from the theory of semi-simple algebras. So, for that purpose, so let us recall a result that we actually seen already. I will reprove it just to emphasize the importance of the result. So, let us say G, H, phi are as before. So, now what we have, so we will just work with that notation. You have H that is inside sitting inside G, and then you have a root system, and then that contains this set of simple roots pi. This pi is denoted by alpha 1 etc. alpha L. So, now each alpha in phi we actually fix this SL2 triple. Okay. So, we will fix that SL2 triple for this set of simple roots. So, given alpha I, so let us say let us take xi, yi and hi to be the SL2 triple. SL2 triple corresponding to this alpha I. Okay. So, in particularly the span of this xi, hi and yi. So, this is isomorphic to SL2C, and the commutators given by the bracket xi, yi is hi, and hi xi is 2 xi, and then hi yi is given by minus 2 yi. So, these are the things that defines this SL2 triple. So, we also kind of have this SL2 triple for each root alpha, but I am restricting it to only for the simple roots. So, that is because we already proved that if we take these SL2 triples, then that actually generate our Lie algebra. Okay, that is our first proposition. So, if we take this xi, yi and hi for I from 1 to L, so this subset, so there are 3 L generators. So, this generates our Lie algebra G. So, what is the meaning of that? G is the smallest subalgebra containing this xi, yi, hi. This hi makes basis. So, let us call G dash to be the subalgebra generated by this, which is denoted as follows: xi, hi, where I arrange from 1 to L. So, this is the subalgebra of G generated by xi, yi, hi, where I arrange from 1 to L. So, now our claim is this G dash should be equal to G. So, note that this H is already span of hi, because hi forms a basis for hi, H. So, that means this H is sitting inside G dash. So, that is very clear. Now, already xi, yi they are sitting inside G. So, the one dimensional spaces also sitting inside G dash. So, now recall a result that we already proved for any given alpha. So, it is enough to prove. Okay. So, it is not hard to see that it is enough to prove G alpha sits inside G dash for all alpha in phi plus. Okay. So, both G plus or minus alpha. So, once we prove that this, then because of the Cartan decomposition, recall the Cartan decomposition. So, G is just H direct sum of all the roots. We know that phi can be written as phi plus disjoint union phi minus. Okay, where phi plus is nothing but set of positive roots, which is defined to be G plus span of pi intersection with phi. So, if we prove both G alpha G minus alpha sits inside G dash for all alpha in phi plus, then we are done. So, we just prove only for the positive roots, the negative roots proved in similar way. So, given this alpha inside phi plus, so we already seen that there exists alpha I inside pi such that alpha minus alpha I is inside phi plus. So, in particularly alpha can be written as alpha I1 plus etc. plus alpha IR. So, such a way that when you take this partial sum alpha I1 plus etc. alpha ik, where k ranges from 1 to r. So, these are all roots, positive roots. Okay. So, in particularly I can use induction on the height of alpha, which is the summation, which is exactly r. So, height of alpha is actually r. So, now using induction on the height, you can easily see that this G alpha must be subset of G dash. So, let's do that. So, if r equal to 1, then there is nothing to prove. So, then there is nothing to prove. So, if we take any r, assume that up to r minus 1 the result is true. So, that means if we write alpha equal to some beta plus alpha I r, and then take beta equal to alpha I 1 plus etc. plus alpha I r minus 1. So, which is inside V plus. So, then by induction this G beta is going to be subset of G dash. So, know that G alpha I r is also subset of G dash, because this is going to be one dimensional space spanned by x alpha I r. Okay. So, since both G beta and G alpha I r subset of G dash, it is clear that if I take the bracket between G beta and G alpha I r, so that is going to be subset of G dash. But note that since alpha is obtained by beta plus alpha I r, and which is also a root, so that means this bracket G beta G alpha I r must be non-zero, and this has to be equal to G beta plus alpha I r, which is equal to G alpha, which is subset of G dash. So, this proves by induction G alpha is subset of G dash for all alpha in phi plus. So, now using similar induction, you can prove that for all alpha in phi plus, G minus alpha is also in G dash. So, now that proves that G dash must be equal to G. So, this is something we already proved, anyway I recalled this proof. So, indeed what we proved that G is generated by these 3L generators, Xi, Yi, Hi, where I range from 1 to L. So, now let us see what are the relations that these generators actually will have. Okay. So, we want to understand the relations that these generators will have. So, later I will talk about presentation of a Lie algebra. Okay. For that purpose, we need to define what is called free Lie algebra and so on. But anyway, we can talk about the relations now, there is no issue. So, that is our second proposition. So, the proposition 2 tells us if we take these generators Xi, Yi, Hi, so then we have the following relations. Okay. So, G generated by this Xi, Yi, Hi and these generators, these 3L generators satisfy the following relations. So, what are those relations? The very first relation, whenever we take Hi, Hj, that must be, the bracket should be 0, and this is true for all Ij from 1 to L. The second condition, if I take the bracket between Xi, Yj, okay, so we have to say how they are behaved. So, Xi, Yj, so that will be delta Ij, Hi. So, whenever I not equal to j, this Hi, Yj that should commute, and whenever Xi equal to I equal to j, Xi, Yi will give you Hi. So, again this is true for all Ij less than or equal to L. The third condition, the action of Hi on Xi and Yj. So, if you act it on xj. So, then we know that we get this Cartan number alpha j alpha I angle bracket and then xj. Similarly, if we apply it on yj, we get the similar thing with minus alpha j alpha I yj. Similarly, what happens if we take xi xj? So, then using SL2 representation theory, one can actually see that whenever you take I not equal to j between 1 to L and apply add xi, so you have to repeatedly apply up to this number alpha j alpha I alpha j comma alpha I, this angle alpha j alpha I, that Cartan number plus 1 you take, and then if you apply it on xj, that should be 0. Similarly, you have for yj's. So, for 1 plus not equal to I, which is not equal to j. So, then if you take add yi and then apply this again alpha j alpha I minus plus this Cartan number plus 1 times on yj. So, that again will be 0. So, these two relations, they are called Serre relations. Okay. So, it was first observed by Serre that so any semi-simple Lie algebra will have these relations. So, the proof that you read in either Humphreys or Carter, so that was actually given by J. Tits. So, he indeed gave this modern proof of how to prove. So, the G is generated by these generators modulo this relation. So, that is actually a big theorem. Okay. Even to state the theorem, we need to understand what is the meaning of generated by something modulo some relations. Okay. So, we will come to that later. But before that, we will just see that these relations are indeed true in our semi-simple Lie algebra. Okay. So, if you go to the relations one by one, you can see that the first relations is somewhat obvious, because H being abelian, that tells that any two element of H must commute. The second relation is also somewhat obvious, that is because to prove second, Hi yi defined to be Hi, so that is fine. So, whenever you take for the second relation Hi yj and you take I not equal to j. So, then what will be the correct root for this, because both of them are root vectors. So, you can see that if you apply any H on this, so then using the Jacobi identity, so it will give you H xi and then xj plus xi H xj. Okay. So, usually I do not put this comma. So, now you can see that this simple computation for any H in H, you get that this is exactly is going to give, this is alpha I of H and then bracket xi xj and then plus this is going to give you alpha j of H and then xi xj. So, that means this is going to give us alpha I plus, sorry, this is yj. So, we have to change this to yj. So, then here we are getting minus. So, it is alpha I minus alpha j of H and then bracket xi yj. So, this simple calculation tells us that if xi yj, even if it survives, it has to lie inside this root space corresponding to alpha I minus alpha j. But since alpha I and alpha j both are roots, we know that this alpha I minus alpha j, because both are simple roots, this difference is not a root. this is something actually we already verified. So, in particularly this is 0. So, that forces that this bracket xi yj is also 0. So, now we proved the relation 2. So, that is done. So, what is about relation 3? So, relation 3 is just a definition of the action of H. So, we have this adjoint action, and then with respect to the adjoint action we can see that so it will act as alpha j of Hi, but alpha j of Hi by definition it is just this Cartan number alpha j alpha I. So, because of this the third relations are true obviously. So, now let us come to the fourth and fifth relation, and I will just verify the fourth relation. The fifth relation is just similar to that. For the fourth relation, so what we are trying to say if we take this particular element in the Lie algebra, that must be 0. Let us look at what is that element. Okay. For the fourth, so we have add xi power minus alpha j alpha I plus 1 acting on xj. So, what is this element? So, this is nothing but you apply xi etc. xi. So, this is minus alpha j comma alpha I plus 1 times, okay, and then apply it on xj. So, this is this element. Note that all these elements are root vectors. So, we know explicitly what it corresponds to, what will be the root if it survives, what will be the root. So, the root or weight of this, okay, let us call it weight because root by definition non-zero. So, weight of this H weight of this element is going to be, so you add alpha I this many times, okay, alpha I. So, whatever this number is minus alpha j comma alpha I plus 1 times plus alpha j. So, this is the number. Okay. So, we want to say that this particular weight is actually not a root. Okay. In that case the root space corresponding to that will be 0. So, in particular this element is also 0. But alpha I and alpha j both are simple roots. So, we already know that alpha j minus alpha I is not a root. Okay. So, then look at alpha I string through this alpha j. We already proved that if you take q to be the max thing that you can add with alpha j, and r is actually the max thing you can subtract alpha j with alpha alpha I with So, let us say q and r max positive non-negative integers, such that you can actually add up to only q and you can add up to only r, subtract up to only r, alpha j minus r alpha I. So, these are all roots. We have seen that this chain is actually unbroken, and there is a formula that connects q and r, q minus r minus q, that has to be exactly equal to alpha j comma alpha I. So, this is the formula that we had. So, this is something we proved using SL2 representation theory. But note that since we can't subtract anything from alpha, any multiple of alpha I from alpha j, so in particularly r must be 0. Since r is 0, that implies that q is nothing but minus alpha j alpha I. So, in particularly up to that this alpha j plus q alpha I will be a root. So, if you add one more, for example like this, so then it cannot be a root. So, then this implies that immediately alpha j, if you add one more of this alpha j alpha I plus 1 alpha I, this cannot be a root. So, because this is not a root, so you can see that this element cannot be non-zero, because if this element is non-zero, the corresponding weight space must be non-zero, which is a root space. So, then that gives you contradiction, because we just observed that this cannot be a root. So, in particularly we proved that add xi, when you apply it multiple times, exactly this minus alpha j alpha I plus 1 times on xj, that is going to be 0. Okay. Similarly, you can prove it for yi's. Okay. This relation 5, I will leave it to you to think about it. It is again the same proof, same SL2 theory that used to prove this. So, this kind of tells us that so this semi-simple Lie algebra is generated by these 3L generators modulo the relations that we actually wrote down 1 to 5. Okay. So, these relations are somewhat very important relations. So, this so later we will prove that indeed this Lie algebra is determined by these 3L generators modulo these relations. Okay. So, that is called SIR presentation of this semi-simple Lie algebra. So, maybe I will talk about that in the next class. Okay. I will stop here, okay, because we are running out of time. Thanks.